All right. So today we'll start or continue with our discussion of the application layer. Did any of you, at least the on-campus students, attend the colloquium given yesterday by Professor Tom Layton? No? Have you heard of this company called Akamai? So Akamai is sort of one of the success stories of the internet, and Tom Layton is the founder of Akamai. And he gave a very interesting talk yesterday. If you sort of heard his talk, he'd tell you about all the problems that the internet has and all of the scalability issues that the internet faces, and how his company solved or attempted to solve most of those issues. And everything that they have done, Akamai, they have done at the application layer. So we'll talk a little bit about what the idea behind Akamai is and how they can do things on the application layer to make the performance so much better. But to do that, we have to learn how to write application layer programs and what all is involved. So today's lecture we'll look at the details of how to write application layer programs. And critical to writing application layer programs, at least on the internet, is this notion of socket programming. So we'll look at socket programming today. So before we start, we discussed earlier that there are, in terms of programming, there's this client-server paradigm of nodes. So now nodes, when we come to application layers, are programs or processes running on hosts. So you have two kinds of nodes, client and server. So we'll see what are all the requirements for a client and a server, and how those requirements are serviced by application layer programming. So what does a client need to do and what does a server need to do? Yeah. So the client initializes the connection to the server. So the client will try and talk to a server. So for that to happen, the server has to do something. So the server has to be listening. The server needs to So this is the first step that needs to happen for two applications to talk to each other. The server has to be listening and waiting for a client to talk. So after that, the next step that sort of happens is initiate connection. So the client initiates connection and the server will accept connection. Once this connection is done, then you can have data transfer in both directions. And finally, you need to close the connection. And the connection closing is like the initiation done by the client in this model. So these are the basic steps that have to happen. Now the requirements of the applications might be different. So suppose suppose the application that we are dealing with is a voice over IP telephone call. So the data that's being transferred in this application, is there any particular requirement, strict requirement? Yeah.
Right order.
Packets have to get in the right order. Why is that a strict requirement?
Because you're probably using Wrttp, which isn't going to check for the order of the packets. And
so you're sort of going one step ahead of where I want you to be. Why are you using Wrttp?
Because you don't have the time. First of all, you don't care if one or two packets drop. It's not.
Okay. So in a voice over IP application, reliable data transfer is not an absolute requirement. You can afford to drop certain packets and still through speech processing techniques you can recover what was sent across the channel. So reliability is not a critical issue if you are dealing with voice over IP or if you're trying to send images. Even if you drop a certain packets, maybe you'll get some distortion of what you were trying to say or the image you were trying to transmit. But you can tolerate some amount of loss. On the other hand, if this client server interaction is of let's say web downloads, you're trying to download a file, then this data transfer has to be reliable. You cannot afford to lose any packet or any corruption of data, right? Because if you lose any packet, if any bits get corrupted, then you won't be able to recreate perfectly the file that you were trying to download. If you're trying to listen to something or if you're trying to view something, then you can accept some sort of distortion or losses. But not if you're trying to download a file. That has to be downloaded exactly. So depending on the application needs, this data transfer has different kinds of requirements. So some data transfer can tolerate loss, others cannot. On the other hand, if you're using, if you're writing this application, a voice over IP kind of application, then the data transfer, another requirement on the data transfer is that the packets cannot be delayed too much. Right? If you're trying to hold an interactive conversation, it's okay if there's some distortion or if some packets get lost, but the packets should not be delayed too much on a consistent basis. If you have to wait 1 second for what you say to go to the other person, then that conversation is not really interactive. So the data transfer for voice over IP has a strict requirement on delay. The packets cannot be delayed too much. On the other hand, if you are doing web downloads, then you can afford to wait a second or two. Often your browser gets stuck, but some amount of delay is tolerable if you're trying to download data. You need reliability, but you can afford delay. On the other hand, for voice over IP, you don't care that much about reliability, but you care about delay. So because of this, the application layer provides different kinds of data transfer mechanisms. That's handled by the transport layer. But the application layer creates this interface to the transport layer to use different kinds of data transfer mechanisms. And for different kinds of data transfer mechanisms, you have different kinds of sockets. And the programming of sockets is a little bit different for both kinds of data transfer mechanisms. So we'll take a look at that. Okay, so if we can switch to the slides. So we'll first answer the question, what is a socket? and how do we use sockets with different types of protocols, different kinds of applications, and what are the associated functions which achieve all of these tasks that a client or server has to accomplish. So we look at sockets in C. So the socket is an application programming interface, and it was introduced in the early 80s in the BSD variant of Unix. So sockets come from the Unix world. They are now part of the Windows world and in any operating system. But their origins lay in the Unix world. Sockets follow this client-server paradigm that we have spoken about. These sockets are handled completely by the application. So they'll be created, used, and destroyed by the application. The kernel or the operating system only provides an interface, a socket interface. The creation and use is completely managed by the application. And like I said, there are different types of transport services which are offered by the socket API. The unreliable datagram service, which is UDP, and the reliable stream-oriented service, which is TCP. So UDP and TCP. UDP is appropriate for a voice over IP or a multimedia kind of connection. TCP is appropriate for a reliable connection. When we get to the transport layer, we'll see that TCP also implements flow control and congestion control. So with TCP, it's very difficult to give guarantees on delays. That's why you need to use UDP for applications that need guarantees on delays, or at least some sort of guarantees. So the socket is, you can think of that, is a door between the application process and the transport protocol that is used by this particular application. So the transport protocol is controlled by the operating system. So it could be TCP with some buffers and some state, or UDP which is sort of stateless. And the socket is the interface between the process, the application program that you write, and the operating system. And which part of the operating system? The transport layer. So the socket lets you access the transport layer to be used by your program. So we'll look at socket programming in two ways: socket programming with TCP and socket programming with UDP. So as we saw earlier, the client must contact the server. So for that to happen, the server process has to be running. The server should create this socket that welcomes or listens for this contact by the client. And this contact is then handed over to the server process that's running on the server side of the system. Yeah.
So let's say that the client contacts the server on port 80, and then the server is willing to accept that contact and creates a socket. Will it move the client over to another open port so that it leaves port 80 open to keep listening, or does the whole communication happen on the same port?
The server moves the client to a different socket, but this listening process is still waiting and listening on the same port.
The port will say that there will be a separate socket open on the port.
I'll show you a specific example. So it's important that you don't confuse between a port and a socket. There is a subtle difference. In TCP, a socket is identified by four different quantities, or 4 different uh, four different quantities: the sender side address, the sender side port, the receiver side address, and the receiver side port. So it's a 4 tuple that uniquely identifies a socket. So on the sender side, where you're waiting and listening, you can have port 80 associated with multiple different sockets. And what distinguishes those sockets is the receiver side IP address and port.
Send data and happen to send it coincidentally from the same port numbers.
But the IP address is going to be the different. So, right? So a socket is a unique identifier on the internet. You can't have 2 sockets running with the same identifier. There has to be something different. Otherwise, it's the same application. Yeah.
Server opens the socket for listening. So socket has also the LAN
Could you speak up?
Yeah, you said the server is opening a socket for listening.
Right.
And so there's an active socket. So there's an open socket for the server side.
Yeah.
But you said that the socket has also the client.
So that socket is sort of waiting to accept a connection. We'll see what that really means. Only when the connection is accepted, then does this socket become live. There is communication happening over the network. So we go back to the slide. You can also think of TCP sockets and UDP sockets as an analogy to circuit switching and packet switching. In a TCP socket, all communication between client and server happens over the same path. There is a notion of a connection. So there is a notion of a circuit. Whereas in a UDP socket or UDP communication, every bit or every packet that is sent out could conceivably take its own path or could go to its own unique destination. So like in circuit switching, what you do is first you set up a circuit, and then you don't have to think about how to transfer data across on that circuit. You just blindly send data across on that circuit and it reaches the destination. So similarly, in a TCP socket, you first set up the socket and then you're just going to transfer data to and fro on that socket. You know where it's going and where it's coming from. In a UDP socket, for each attempt at communication, you have to uniquely specify where it's going and where it's coming from. There is no notion of a connection in a UDP socket. So it's like packet switching. A packet just goes out of the network and it's routed along. Similarly, with UDP sockets, every attempt at communication is sort of its own entity. So let's look at the socket interface in more detail. So TCP provides a reliable in-order transfer of bytes between client and server. So the socket is an interface between applications and a network. The application will create the socket. The type of socket will dictate what style of communication you are going to use. So whether it's a UDP socket or a TCP socket, that determines whether the connection or the communication is going to be reliable or best effort, and whether it's going to be connection oriented or connectionless. So think of the circuit switching and packet switching analogy. Yeah.
So is it sort of the same that you're saying that TCP uses virtual circuits and UDP has dynamic routing? Is that true?
No, that's not true. Because underneath at the network layer, we don't know what's going to happen. It's just the way the application views this pipe. So once you have this socket configured, then the application can pass the data to the socket to be transmitted over the network. And the application can also receive data from the socket, transmitted through the network by some other host. So TCP and UDP have different kinds of sockets associated with them. So the TCP socket is called sock stream. Sock stream gives you a pipe which guarantees reliable delivery. So every packet that is transmitted from a server will reach the client. Additionally, TCP also guarantees in-order delivery. So the underneath the application layer and the network layer, these packets are still being forwarded on the network using the datagram model or the packet switching model. So different packets can take different routes. And some routes might be longer than the other. And what you can have is at the end host, you can have out of order delivery. So I send 2 packets in the network, packet 1 and then packet 2. But the network delays packet 1 so much that packet 2 reaches before packet 1. But what TCP will guarantee is that if you send packet 1 and packet 2 in a particular order, I will deliver it to the application in the same order. Because if you don't deliver things in the same order, the application can get confused. I mean, if a second sentence arrives before the first sentence in a web page, the meaning would be totally different. The TCP will guarantee in-order delivery. So, and like I said, TCP or the sock stream is connection oriented. So think of that as a virtual circuit, and it's bidirectional. So once this socket is established, the packets go to the same destination from the source. Each packet need not specify where it's going. Once the connection is established, packets just flow on this pipe between the source and destination. Sock dgram or datagram is the UDP socket. UDP offers no guarantees at all. Unreliable delivery, packets might get lost in the network. If they do, sorry, UDP is not going to do anything to recover the packets. If packets do get lost in a TCP socket, TCP will recover the packets by retransmission mechanisms, but TCP will not do anything like that. UDP gives no guarantees of the order of delivery. If the network changes the order of packets, then UDP will deliver them out of order. It is the responsibility of the application to recognize if there's a problem and fix the problem. The transport layer, UDP, will not do anything to fix that problem. There is no notion of a connection. The application has to indicate destination for each packet. So again, when you see here, these packets from the same socket can go to multiple different destinations. So this socket, you have created a port to the network, but every time you use this socket to send data out, you have to specify the destination in UDP. In TCP, once you set up the socket, you don't have to specify the destination. It's known where the socket is going. But in UDP, each time you try to send data out, you have to specify explicitly where it's going. So it's connectionless in that sense. Okay. So now let's get down to the details of the functions that we use in C to do socket programming. So the first function is creation of a socket. So the function is socket. The parameters are domain, type, and protocol. The return value is the socket descriptor or an integer. It will return -1 if the socket creation fails. Otherwise, it will return an integer which is the socket descriptor or the file descriptor. Domain is the communication domain. So it specifies over what kind of network this socket will operate. So typically we use PFINet, which is the IPv4 protocol. So that's telling the operating system that we are going to use an IPv4 network to communicate using this socket. Type, which is the second parameter, is the communication type. So the two main types are sock stream and sock datagram. There are other values which are rarely used or obsolete. So there are other kind of transport protocols which typically we don't need to use in an application. Yeah.
You said this was first developed in Unix. Is this OS dependent? I mean, can you do this in different versions of Unix and on Windows and etc.?
There are minor variations, but the big level picture is the same. The socket interface is essentially the same. So the Windows implementation, very similar. But what we are talking about has its roots in BSD. Another question? Protocol, again, specifies the protocol that's going to be used. So if you log into any Unix machine, you can see this file in /etc called protocols that gives a protocol and ID mapping. For IP, the internet protocol, this mapping is 0. So this protocol value is typically set to 0. There are other protocols that you can use, and if you look at that file, you'll get an idea of what other protocols can be used. So this is simply creating the socket. So right now we have not specified whether this socket is going to be used by a client or a server. We have simply created an interface to the operating system, giving us access to a particular kind of transport layer protocol. So from a socket view of the internet, these sockets are going to talk between applications. And applications are uniquely identified by what? The host where they are running, and what we sort of alluded to earlier, the port on which they are running. But the host name also is not unique. It could be ambiguous. So there are host names, valid host names, which resolve directly to one machine, my workstation or some workstation by the author of the textbook. Or there are host names which resolve to multiple different machines or multiple IP addresses. Also, you can have the situation where one host has multiple IP addresses. So your machine could be connected to the Ethernet, to the wired network, and it could also have a wireless card, and it will have a wireless IP address. So each host can have multiple IP addresses. When a packet arrives at a host, each host also has these ports. So port is a 16-bit value. So each host will have 65,536 ports. and the packet goes to a particular port in a host. And we'll see what's the difference between UDP and TCP and how these ports relate to sockets. But to identify a socket uniquely, you need not only the address, the IP address of a host, but you also need the port value where the packet is supposed to go. So some ports are reserved for specific apps, like all of you know that 80 is reserved for HTTP. 20 and 21 is reserved for FTP. One is the FTP control channel, the other is the FTP data channel or data port. Typically, the lower numbered ports are reserved for specific kinds of applications or well-known services. There is an RFC which describes which ports are reserved. For application layer programs which don't have root permission, you can use higher number ports. And when you're a client, then you typically don't need access to these reserved ports because you're not going to be sitting and listening and waiting. These reserved ports are used mainly for server applications. So when you're a client, you don't need access to a specific port. The OS will provide you with a port on demand. Once you open up a socket, the OS will see which unreserved port is available and will assign you that port. So the difference between a port and a socket is this, the analogy between apartments and mailboxes. So your application is like the apartment. You want to send or receive data between applications or send and receive data between addresses. And how is that achieved? Well, your apartment building address is the IP address and your mailbox is the port. We don't worry about the network, which is the postal system. The socket is the key to the right mailbox. So there's a difference between a port and a socket. Okay. So now we look at how this key or how this socket can be associated with a unique port or a unique mailbox. So the bind function achieves this. So the bind function will associate a socket with a particular port and can exclusively reserve that port for use by a particular socket. So the previous function that we saw simply created a socket. It did not have any notion of which port this socket is going to be associated with. The function bind achieves that. So again, the bind function has 3 parameters, and the return value is the status. If there's an error in binding, the status return is -1. If bind fails, the parameters are sock ID. So sock ID is the socket descriptor which you got from creating the socket. So the first step that you did was you created the socket, the return value gave you a sock ID. Now you use that sock ID with this bind function. So the first parameter is that socket ID that you just created. Then next parameter is the struct sock address. So sock address is the IP address and port of the machine that you want to associate this socket with. So IP address usually is set to the local address, and port is what you specify. So this struct will contain both the IP address as well as the port number that this socket will get associated with. And this function is typically used in the server. So your web server, for instance, will have a line something like this, where the address port would be 80, and the web server will try and bind itself to port 80. And like I said, bind is typically used for the server. So, and bind is kept for both types of sockets. So one instance where it is kept is when your application is simply a client application. So client application need not bind to a specific port. Is there any other situation where it can be skipped? For both TCP and UDP. Well, if your socket is going to be used only for sending, so if it's client, then there's no need to bind. But if the socket is going to be used for receiving too, then you have to bind. So for a datagram socket, if you know that it only has to send, never receive, then you don't need to bind that socket to a specific port. Sock stream, again, if you're the client, in let's say a web server or a web server architecture, web server web client architecture, your browser is the client and the server is the web server. So your browser will initiate connection, right? It will initiate connection and then data transfer is going to happen. But this data transfer happens in both directions, right? Your web browser will send a request to get a particular web page and then the web page gets returned. So data is flowing in both directions. But still, in the datagram socket, if you were only sending, then you didn't need to bind. But in the stream or the TCP socket, even if you're sending data, you don't need to bind if you're the client. Why? Because when you initiate the connection with the web server, at that point, the web server gets informed which port you're coming from. So the whole idea of binding to a specific port is to make the address well known to the network. So when I'm going to a website, I don't have to hunt around on all the 65,536 ports to locate the application which is the web server. I know that the web server is supposed to run on port 80. So I know how to talk to the web server. But the web server also has to talk to my browser. It has to receive information from my browser and it has to send information to my browser. But the web server doesn't have to hunt around which port my browser is running on. Because when the browser initiates this connection, the browser will tell the web server that, okay, I'm running on port 14,582. So in the stream scenario, in the TCP socket, if you're a client, you don't need to bind to a particular port. As you need the socket, as the operating system will provide you with a particular port, and that information is relayed to the server. Is that notion clear? Why? Yeah.
But the client still needs to know the socket you're sending, server socket. Does the client need to know that?
No, the client only needs to know the port.
Yeah, that's what I meant.
Yeah.
Of the server.
Yeah, so because the server is running a well-known service. So a well-known service like a web browser or a mail server. That's why these ports are reserved, and that's why the server needs to bind to these particular ports. So your mail program will bind, your mail server program will bind to port 25 because everyone else expects it to be there. But your mail client, when it starts the connection, it can use any port. When the connection happens, then that information is exchanged. Yeah.
If an application binds to a port and for some reason or another the user doesn't close the socket, how long does that binding last? Does the operating system have to restart?
The operating system has to yeah. So it also depends on your programming practices. If your program crashes, there are ways to cleanly code that you release the port when your program exits. Otherwise, the operating system will look for a timeout and then release the bind.
If you look for a timeout for the application, so if you try to send a signal to the application, if it doesn't respond, it'll follow it notice.
So that's implementation dependent, or different operating systems implement it differently. But it's finally the operating system is responsible for cleaning up if your application is not coded properly. So, okay. So now we have looked at those two functions: creating a socket and then binding the socket to a particular port. So that happens at the server. To initiate a connection, what do you need to do? Well, again, as we said, in the UDP sockets or the datagram sockets, there's no notion of a connection. So you don't need to do anything. But we need a connection setup process for the TCP sockets. So the connection will occur between two kinds of participants: the server, which is the passive participant, which is waiting for an active participant to request a connection, and then the client, which is the active participant. That's the application that will initiate the connection. So how does this setup work? Well, the passive participant will set up and listen and wait for incoming connection from an active participant. In step 2, the active participant will initiate a connection, request and establish a connection. Once the connection is accepted in step 3, then data transfer can happen. So the passive participant is ready with its listening socket and waiting. The active participant then creates a socket. So this is the client which has created this socket, and then the client will initiate a connection with this socket. So now, as I said earlier, a socket uniquely determines the applications between which communication is happening. So once you create this connection, this socket, then the passive participant or the server will create another socket and will hand over this active participant to that other socket. So that frees up the socket which is used for listening. So then the next client can come in, initiate a connection and get its own socket. So another client comes in, does the same step, and it's handed over to another socket. So the passive participant still has the original socket running on the same port. There is a temporary connection when this socket talks to or speaks with this socket, the listening socket. The temporary connection is used only to create another socket at the server or the passive participant and hand over the client to that newly created socket. So that's the way a server works. There's a socket dedicated just to listening, and then fresh sockets are created for data transfers. Okay, so now let's go through the connection setup and what all is done. Yeah.
A server like CNN, there's so many millions of people coming.
Yeah.
So isn't the number of sockets limited by the number of ports?
So a server like CNN is not running on one machine. It's running on a cluster of machines. Also, well, it goes back to what Akamai does is, when you think you're going to CNN, you're probably not going to CNN, but you're going to some sort of a content delivery network or a cache website. So all those millions of users are being distributed across many machines. They don't go to a single machine, otherwise it can never work, it can never scale. Each machine has its own limitation of 65,000 sockets, and it works with that. And in fact, the web server also imposes a stricter limitation: how many forked web processes or forked servers can run. You had a question? Okay. Yeah.
If there are two clients connected to the server at the same time, and before the first socket is moved by the server to another socket, and how can and the second client come, and now how is the initial connection of the second client will fail?
No, so that's what we'll look at right here. So if we move to the slide, the first function that is called by the passive participant is listen. So you have set up the socket, you've bound it to some port, and then you call listen. What listen does is, it listens on the socket with a queue length. So this is the number of active participants that can wait for a connection. So you can set this queue length to 16. So 16 clients can simultaneously request a connection. The first one is served while the others wait. So every listen also has a queue or a buffer associated. So that's the first function here. So the passive participant is doing what? It created the socket, it bound it to a port, and then it set it up for listen. So this function achieves the listen. Then the next step is at the server side, accept. What does accept do? The return value of this function is a socket descriptor again. So this is the new socket you're going to hand over the communication. So if it's successful. And what are the parameters? Well, parameters are sock, which is the socket where you were listening on originally, the name of the active participant. So the active participant will have its IP address and its port number, and that's this struct sock address. So this identifies which active participant tried to connect to me, and now I'm going to hand over this socket of the active participant to a new socket. So henceforth, the communication will happen between this S, the new socket that is created, and name, which refers to the remote client which initiated this connection. So is this step clear? So this is all that's happening on at the server side. Now listen is non-blocking, so it returns immediately. If you call this listen, it will return immediately and you can proceed with the program. Accept, on the other hand, is blocking. It will wait for the connection to be established before returning. And this is important because this this is hiding what's going to happen underneath in the transport and the network layer. The connection has to be established between these two sockets. And so TCP has to do its handshaking and things have to happen in the network. So this will take a finite amount of time. So this blocking nature of accept is a very important thing when you write your own programs. The connect call is the initiation of this connection. Again, status is 0, which is the return value of this function if successful, -1 otherwise. Sock is the local socket that you are going to use for the connection, and name, or the name, is the struct sock address, which is the remote address of the passive participant. So when you are initiating this connection here, you know your local socket descriptor, but at the remote end you have to give the remote address and the port number. So IP address of cnn.com and 80. Yeah.
Two questions. On the previous slide, you had the name length as a pointer or reference rather than as an integer. Was that a typo?
That's probably a typo.
And
Yeah.
secondly, why do you have to pass in the length, the new length?
Because different you can have different kinds of socket addresses. Typically we deal with socket address in, which is the internet socket. You can have different kinds of networks which will have different lengths. So you need to specify that. Yeah, this is a typo. Sorry. Yeah.
That should not be a typo because the number has to be filled in by the operating system.
Yeah.
So that should be a point. This is set by OS upon return.
No, for except it has to be set appropriately before the call. Okay, right. Yeah. It is adjusted by the OS upon return, right? Yeah. So it's not a typo. I had it right. So you set it appropriately before call, and if there's a change, then the operating system changes it. Whereas with connect, you know what it is. Yeah. And connect, like accept, is also blocking. So it will return only once the connection has happened. So once this connection is established, then data transfer can happen. And data transfer happens using functions to send and receive data. So for TCP or socket stream kind of connections, the function that is used is send. The return value of this function is count, or the number of bytes which are transmitted. If there's an error, then it will return with -1. Sock is the socket you're using to send the data. The buff is the pointer to the buffer, which is going to be transmitted. Length is the total length of the bytes that you want to transmit. And flags are some special options. You can make the data urgent and things like that, but it's usually set to 0. So to send data, you simply call this function send, and it will push data onto the socket, and it will get transmitted across the network to the receiving end. Now so once the connection is established, then this data transfer is happening in a bidirectional manner. So both client and server will call the same function. So from now on, the behavior is symmetric. Similarly, you have this function receive. The return value is the number of bytes which were received. The parameters are sock the socket on which you are receiving the data, the buffer where you'll fill the data out, where you'll send the data to your program, length again, number of bytes received, and some special options. So calls for send and receive are also blocking. In a UDP or a datagram kind of socket, the functions look very similar, but the difference is they have two additional parameters. And these parameters define where the data is going or where the data is coming from. So in TCP, once you establish the socket, you know where the data is coming and going from, because there is a notion of a connection. With UDP, since it's connectionless, with every call of send or every call of receive, you have to specify exactly where it's going. In TCP, the socket took care of that, of the destination or the source. But here, you need to explicitly specify the destination or the source. Otherwise, they look pretty much the same. Very similar functions. When you're done using the socket, you have to close the connection. So you close, the function call is close, and the argument is the socket descriptor. And as it's clear, it's only used for a sock stream kind of socket, which closes that connection. For a datagram, it just frees up the port which is used by the socket. The struct sock address, which defines the address of a remote socket. It has two parameters. The family of the socket address that you're going to use, and once the family is specified, that determines how the remaining 14 bytes are being used. So for the internet specific socket address, you have the family which is used is AF INET, and it has three parameters. First is the port number, second is the internet address, and then you have zeros which are unused, because for the AF INET family or the internet specific socket address family, you don't need to use all the 14 bytes which are defined by the struct. So port is how many bytes? 65,536, which is 16 bits or 2 bytes. The IP address is 4 bytes. So that's 6 bytes. 8 bytes are free. There's another issue which has to do with address and port byte ordering. Different machines or different operating systems use different word orderings. There's a little endian where you place the lower bytes first, and then the big endian where you place the higher bytes first. Now these machines need to communicate with each other over the network. So the question is, which order should you place the bytes in? Because if the machines interpret it wrong, then you can confuse part of the port address as part of the IP address, and half of the IP address will become the port address, or vice versa. So they have to communicate and interpret this stream of bits in the right order for this network communication to properly happen. So big Indian machine sends the data across. The little Indian machine will not interpret it properly. So for instance, the IP address 128.119.40.12 will get interpreted by the little Indian machine as 12.40.119.128. So how do we resolve this problem? Should we specify in our protocol or in our message which kind of ordering are we using? What kind of machine it's coming from, or is there a different solution?
We select one of those two and use the common.
Yeah, so the solution is you have something called a network byte ordering. And network byte ordering is always big endian. So when you're communicating over the network, it is assumed that the byte ordering is going to be big endian. So any words that are sent through the network should be converted to the network byte order prior to sending and back to host byte order once it's received. So again, should the socket perform this conversion automatically? Not really. And since some machines already have this byte order in the right order, this socket code should not be doing things which are not needed in half of the machines. So if you're writing portable code, how do we avoid writing two versions of the code of the same program which are going to run on little endian or big endian machines? Well, Unix provides this byte ordering functions which convert host to network and network to host byte order, both for long integers and long as well as short integers. On big endian machines, these routines will do nothing. So it's like a no-op. You send in something, you'll get back the same thing. On little endian machines, they reverse the byte order. So whenever you're writing code, it's always a good idea to call this function before sending out data on the network. It will ensure that your data is in the right network byte order. So one thing that we saw, that many of the functions we saw will block until a certain event has happened. So accept will block until a connection comes in. Connect will block until the connection is established. Receive and send block until the data is received or is pushed out into the transport layer or the sockets buffer. For simple programs, blocking is convenient. But if you have complex programs like a web server which has multiple connections, which has simultaneous sends and receives, this blocking will make the program very inefficient. So how do you deal with blocking calls when you're writing network code? Well, there are different options. You can either create a multi-process or multi-threaded code, or you can turn off the blocking feature of these calls and use the select function call. So are you familiar with the select function call? Have you used select? Have all of you used select? Or so you know what select does. So select essentially it'll what you do with select is you we'll see how select works. You give to select a set of file descriptors, or in our case sockets, to check. So you want to check certain sockets if they are read ready, certain sockets if they are write ready, and certain sockets if an exception is registered. Select will return once that condition has become true. So instead of those blocking calls, you make them non-blocking, and then you just monitor them using select. And whenever any socket is ready for what you want to do, select will inform you of that, and then you can process that socket. So select lets you deal with these blocking calls and helps you create complex, efficient programs. So the details of how do you select are given in the slide. There are other useful functions which I use with socket programming in Unix and C. Yeah.
There's no correlation for the select function in Java.
No. So I'm not going to go through socket programming in Java. The book has two really good examples of writing a client and a server program in Java. The slides that I put up on the website, they also have detailed step-by-step implementation of the client and server in Java. So you can go through that. C socket programming we went through. So it's your choice how you do the project in C or Java. And yes, other useful functions that you need in C for socket programming are listed here. Let's see. So someone had a question of what happens if you have a rough exit from a program. How long would the port be bound to a certain socket? Well, eventually the operating system will release the port, but to reduce the likelihood of this problem, you can use signals which ensure that your program exits cleanly. The sample code is given here of how to ensure that happens. You can go signal.h and in socket code insert these two lines, sig term or second clean exit, which exits the program and releases the port. So we'll stop here this lecture, and in next lecture we'll start looking at some application layer protocols, and also we'll take a look at content delivery networks and the idea behind caching and what Akama is all about.